Hello and welcome back. In our previous tutorials, we explored various deep learning models for building footprint extraction from aerial imagery. Among them, the pre-trained unit model stood out with the highest accuracy, especially in terms of the boundary intersection over union. As shown here, the pre-trained unit model achieved remarkable accuracies, especially if we look at the boundaries. And the boundary I owe you is 0.5, which outperformed the other models, such as the standard unit and the DeepLab version 3 plus, which scored below 0.3. Okay, but just looking at these metrics is not the whole story. So in this tutorial, we go beyond performance metrics and we try to open up the black box of this best performing model, that is the pre-trained unit model. So here, we are going to learn how to apply explainable deep learning techniques to see what the unit model is actually focusing on when it segments buildings in aerial imagery. Right, so deep learning models such as this unit are very powerful, as we have seen, but they are opaque. In other words, it is very difficult to understand why the model detects a building in one location, but then it can miss the building in another location. So to answer that, we are going to apply the Grad-CAM, that is the gradient weighted class activation mapping technique, which is a type of explainable deep learning method. So this technique generates visual heat maps that highlight the parts of the image that influence the model prediction the most. So by the end of this tutorial, you'll be able to visualize and interpret the unit model decisions. That is making your segmentation workflow not only good in terms of accuracy, but also transparent and a bit explainable. Right, so let's get started. As usual, we do the installation of our libraries, and then we import the necessary libraries. We do our setup, and we do the necessary loading of the data sets. I'm not going to go into this part because this is what we've been explaining in the previous tutorial. So loading the imagery and the corresponding vector file of the building footprints, and then creating the patches from the image and mask, and then splitting the data, and then creating the data loaders, and then running the pre-trained unit model here. And then, as usual, do the training, then visualizing the results, and then we predict the full image mask, and then finally we do the evaluation of the predicted image, and then display this image as we've done in the previous models. Right, so I really want to focus on the part where we actually try to use the Grad-CAM in order to understand the decision of this pre-trained unit model. Right, so let's break it down here with the Grad-CAM. Right, so as I said, the Grad-CAM help us visualize the region in the input image that contributed most to the model's outcome or output. So here's how we implement it. So first we are going to define the GradCAM class here. So this is the GradCAM class, and we specify the target convolutional layer, the layer that we would want to target. Okay, and then we are also going to use the PyTorch hooks. So these hooks are the ones which we use to capture the feature maps during the forward pass and the gradients during the backward pass. So we have the forward pass and the backward pass. Right, and then we compute the weighted combination of these gradients and activations to create a heat map that highlights the most important regions of the predictions. So the final output is going to be a normalized visualization of the model attention. So this is going to help us interpret where the model is focusing on when it does the segmentation. Right. After that, we can also after running this code, we then visualize the GradCAM's models outputs. That is, we overlay the GradCAM on the predicted mask. So here, simply this code is going to show us how we do it. So first, we want to apply this GradCAM to only 3 random validation samples. In other words, we want to take an input image and its corresponding reference mask. So remember, we have these images split into 256 by 256 pixel size. So we are going to take the original orthophoto image, okay, and then the corresponding mask, and then we are also going to get the predicted binary mask, that is the predicted building footprint with the background, and then we also want to apply now the GradCAM, and then we generate the heat map. Okay, so we apply the GradCAM here so that we generate the heat map. So finally, what we are going to have is the original orthophoto image. Then we have our reference or ground truth mask. Then we have our prediction, the predicted segmentation mask, that is the predicted building footprint mask. And then finally the GradCAM heat map over the prediction. So if we run this code, this is what we get. Okay, so first, this is the first result. Remember, we just picked only 3 samples. You can pick more samples if you want. So here we have the original image, and this is our reference or ground truth mask. Then this is the predicted, and then this is our GradCAM on the predicted mask. So as you can see, this GradCAM is highlighting areas where we have a lot of intensity in terms of the prediction. Okay, so let's look at the first sample. So here the GradCAM strongly highlights the building rooftops area. So these red or orange areas and yellow zones also align well with both the predicted and the reference ground truth mask, okay, as you can see. So this indicates that here in these samples the model is confident and it's attending to the correct features. So this is a very good, clear visual evidence of effective learning. Right, and but we also see very important outcomes here, that there's a bit of this background. Okay, this background influence affecting, although this one does not affect the final results, but probably it's having some effect, some noise effect in the image. Right, if we look in the second sample, here we see that there's a strong prediction here in this part of the building. Okay, this building rooftop. So this is quite strong and effective. But there appears to be a lot of scattered results here in this model result. Yes, the model still detects the buildings, but some of the attention spills into irrelevant areas like the ground, or maybe the shadows. Okay, as we can see, there's a lot of problems here, probably because there's this small building which is influencing, which is missed. So this suggests uncertainty, because perhaps the image contains a problem of say low contrast features, which is this road background is as you can see, is a bit similar to this rooftop. So this is causing a lot of problems here. Okay, so this Grad-CAM result reveals not where only the model is getting right, but where it is unsure. Okay, so I think for the next part, we need to make sure that there is a bit of contrast between these buildings, rooftops, and the background. So this is very, very important. And then if we look at the last sample, we see that we have got a building here, which interestingly, in the ground truth mask, in the reference mask, it's missed. You see, this is missed completely. But the pre-trained unit model picked this building rooftop. And again, the Grad-CAM is also showing very good result, showing that the model did a good job in identifying this building. So this is a positive. However, you should also note that there is also a big problem of the background. So where we have a dominant background, and this background appears similar to the rooftop, then we are having here some noise coming up. So here what GradCAM is telling us, that this is also having an effect in the model outcome. So this kind of insight is critical when evaluating model robustness, especially if we are to look into more real-world geospatial applications. That is to do with, say, a building footprint or a road detection. Right, so this is all about this lab. So we have explored how GradCAM can be used to visualize attention in semantic segmentation. We have also integrated the GradCAM into this unit pipeline, and then we applied it to building footprint extraction from aerial imagery. And we've also interpreted these results so that we assess the confidence of the model. So if you are building models, especially when you're using the deep learning models from Earth observation datasets, or you're doing any work that is to do with urban planning. So these explainable machine learning models are very important, so that you can also help explain to other stakeholders. So this build stakeholder trust and accountability. Right. So if you have any questions or feedback, please drop this in the comments section. I would love to hear from you on how we are using these explainable deep learning methods in your work. So thank you very much for watching. I will see you in the next tutorial.